Okay, so I was told it's good to start. Hi everyone, how's it going?
Good.
Okay, yeah, I mean it's Sunday. Thanks to the organizer for inviting me. I'm going to tell you, give a talk on ethical dilemmas in scientific discovery. A little bit in how I see it as a practicing scientist. So to get started, the purpose of the talk is really just give you a broad overview of what are maybe some potential problems that I think we have right now. I don't think there are concrete solutions. I think we probably have solutions, but we don't know how to implement them. And that might be your job, right? Hopefully it's something that creates some talking and thinking. Just a little bit about me. I'm PI at the Chemical Cognition Lab, University of Toronto. Chemical engineering, also Vector Institute. We have a human-centered mission to empower engineers and scientists to tackle chemical problems using robotics and AI. Prior to that, I was working at Google Deepmind as a research scientist. This is the group in action as a GIF. And the type of stuff we do is kind of like molecules and AI. We care a lot about interpretability, specifically of scientific problems, and very soon we'll also have a lab with robotic manipulators. So we really think about how do you automate a lot of the hard problems in doing experiments, which is often manual labor. Some extra points of connection. One NGO that is close to my heart is Clubes de Ciencia. More than 10, 11 years. There's also SALA, it's an AI conference in Latin America that's happening next week in Quito. There's a bunch of protein work that you're not going to see today. There's the UofT connections. So I have a first activity because I want to see what people think about this. Yeah, if somebody's taken any courses, you would probably be like, I know what this is. So what I want you to do is walk to somebody you don't know. I already know who knows who based on spatial proximity. So just talk to somebody you don't know, and this is your prompt. So I'm going to give you 4 minutes. Talk to somebody you don't know. Typically this means spatially, it's Sunday, get up. You guys been sitting 2 hours. Talk to somebody you don't know. Okay, that's good. Okay, we're going to close up the discussion. I want to get a quick survey of what you talked about. So I'm just going to point in general directions and just talk about whatever you talked about. Try to just keep it concise, less than a minute, because I want to get at least a few responses. What did you talk about in that direction?
Well, we talked about authorship in AI with the rise of AI and how it would impact citations or how we know who actually wrote some of the material that are in reports or the scientific articles. And then we also talked about eugenics and that kind of being on the edge of I know some people find it immoral, they don't know true ethics, and it's a discussion right now, so that's mainly the thing.
Okay, so authorship, attribution, and genetics or genetic engineering, right? Somebody in that direction.
I could say that with my new friend we discussed vulnerability, and in particular how the research around ancient DNA is using data that is basically extracted from First Nation population without their consent, or saying, hey, we can use your DNA to study if you're more likely to develop some disease, and then the researcher moves on to another university, and the research is never produced, but the data is collected.
Yeah, that's a big problem, right? I think there's a connection here with genetic data. Genetic data is like so connected to people, so like obviously there's a lot of risks there, right? Anybody want to participate? Yes.
There was just an issue of sort of reliance on childcare and the intertwining of like child development and LLMs, and how you're not supposed to really use it if you're under a specific age, but there is usage regardless, and then the possibility of jailbreaks, and then children getting, I guess, involved in topics that might not be age appropriate for them, and then also the development of putting those systems in toys that are basically used, I guess, as a form of childcare and like helping children develop without, I guess, a lot of parental involvement as well. It's just like the overall sort of ethical dilemma of that and the implication it has on their development and like how it affects them as an adult.
So I think that's like a really interesting point, because it kind of points at one of the problems of like, we just don't know everything, and these things affect lives, right? And so how do you control, how do you like make decisions when you don't know things, right? Okay, we got
Can I ask?
yes.
So something else that I think is very interesting when it comes to AI and ethics specifically, with AI, everything is black and white. There is no gray area. Versus in real life, we give people grace, right? AI doesn't have any grace. You are already here, you're either here or you're either there. There is no ambiguity. There is like, everything is just like so cutthroat. I think that is the whole point of ethics, when you have empathy and give people some room to wiggle, and I feel like AI doesn't have that.
Yeah, so you're talking about like sort of like a human part, right? How do you capture the ambiguity sometimes, or nuance that is needed? Okay, the dilemmas I'm going to talk to you about, and these are the ones I think about because I do like chemistry stuff. Interpretability. Often, how do we know that what we know when we make a discovery? How are we actually certain? I think that connects a little bit to this point of like, if we're making a claim, how do we know that this claim is actually true? Generative AI, it's how do we can now supposedly make stuff and supposedly like make things that are really bad or good, and how do we do it with these new tools? And sort of like when you're actually doing a scientific discovery campaign, like what is like, you have a lot of data problems, and sort of what are the real constraints that you might have in a scientific discovery campaign. So let's just start with the interpretability part. I think it's good to just have a few definitions of interpretability. There's many ways of saying it, but I like the last one the most. It's sort of like the science of understanding AI models from the inside out. These are all just kind of like different ways of saying like we just want to know why decisions are made. And so one of the cases that I care about is one of the things I study is olfaction, so smell. Smell is our chemical sense, in the same way that webcams are sensors for light, or nodes is a sensor for molecules. And so one question I might have is like, and that people sometimes are not able to answer, is like, why does a molecule smell like rose? Why does it smell like vanilla? Why does it smell like something else? What part of the molecule is making that? So it's a mechanism, kind of like we don't know why things smell. So typically we'll build a model and it'll like answer this question. And and the way that people historically have come up with these explanations is, there's this Boolean's rose rule. It's like from 1973. It first appeared in like some like written letter that Boolean sent to one of his friends. It's really hard to track down the actual like scientific paper that talks about it, but like he's sort of found this pattern that, well, he says like, when you have this group of molecules and it's close to this other carbon chain and it's close to this other group, then it tends to smell like rose. So it's like this, combination of concepts. And so what you would have to do if you really want to test this like theory is you would have to kind of make new molecules that fit this like pattern and see if it actually gives you new rose-smelling molecules. How can we do this like now? How can we find these explanations now today? Especially we have AI models, supposedly we have interpretability tools. Can we just extract, kind of these rules? One of the things we can do is, and one of my favorite things to do with any modeling is use linear models. Linear models are great because you can grab weights and you can kind of interpret them. And typically higher values in the weights are going to tell you that they're important, and the sign is going to tell you good or bad. And so typically we can represent the molecule as does it have this graph, does it have this other subgraph? That's one way you can represent it. And if we train a model to predict this, we might be able to get, how important is it? We might be able to recover sort of this explanation. And this is how you would do it. You just get your model, and then you can highlight the parts that actually are relevant. And you might be able to build that explanation based on that. This is still hard because what can happen is these models are trained on data, and data is not perfect. So what can happen is we can have a co-occurring feature. In this case, we have this little ring, and it co-occurs with the ring plus this extra element. And if the data has this co-occurring element, our model might, quote-unquote think that it's actually because of this bigger element instead of the ring. And so when we actually get a new data point, and it doesn't have this bigger element, it might be an incorrect prediction. It might give you a wrong explanation. Your model is trained on biased data sets, and no data is perfect, so there's always going to be biases. So that's one problem. This is the same problem that people have found in computer vision, where you have a classifier that can sort of predict, that this dog was a wolf, and basically if you use some interpretability tools, it turns out that the model was taking into account basically the snow to think it was a wolf. This is a spurious correlation. Sometimes there's extra information that our models are focusing on and that give it signal to make predictions. And it only happens until later, right? Other problems is our models are not perfect. So can you trust a model that does not give you perfect predictions? And our explanation is supposed to be, if you have a perfect model, is a model going to give you perfect explanations? Likely not. You could also ask the question, if you have a really bad model, random model, is a model going to give you random explanations? Turns out some models can give you good explanations even if they're random. So it's just, this is just an extra layer of complexity. The other part is we're not often dealing with linear models. We have more complicated models. And so if we apply an interpretability tool, now we're kind of relying on an approximation. And so now you have another problem that even your tools are kind of imperfect. In general, there's just a lot of problems, right? Imperfect models, imperfect techniques, imperfect data. And ultimately, we're trying to venture into the unknown. And so it's how do you, that's the question that we want to solve is how do we make predictions into the unknown? So that's just to give you a snapshot of some of the problems. In general, my bell pepper spicy take would be that kind of interpretability sounds nice. It's always nice to say that something is interpretable. In general, it's imperfect. But I think you really have to rigorously test if your interpretability is doing what you think it is doing. Because not often it's doing what you're doing for all these reasons. So in general, I think we just need to spend more time, if you're using interpretability, thinking about it. Is it useful? Sometimes it's not useful. People hate heat maps. If I give a heat map of a molecule to an experimental person, they don't really care. But it sounds good to have the interpretability part on a paper. So often there's a lot more work in making things actually interpretable. On generative AI, so one thing that we can do in molecule space is we can create new molecules. We can train models to convert a molecule into a continuous vector and decode it back. So this gives us the same molecule. This is work that I published with other co-authors, with other authors in 2018. Probably the first generative AI algorithm for chemistry. It's a variational autoencoder. And some of the things you can do with this is it gives you a local geometry. So if I put a molecule like ibuprofen and then look around it, you're going to find molecules that kind of look like ibuprofen. So it gives you kind of things that are kind of similar. Just having this capacity gives you a lot of things implicitly. So for example, maybe I don't have ibuprofen in my house, right? Like my head hurts and I'm like, I need ibuprofen. But I might have another chemical in my house, isobutylbenzene, right? And you're like, how do I get from this molecule to this other molecule? If you're a chemist, you might be able to do sort of chemical synthesis to sort of get ibuprofen when you don't have it, right? So one thing you can do is you can put these two molecules in this space. You can say like, how do I move from one space to the other? How do I move, how do I create a path? And because everything is kind of local, you can kind of find small changes that arrive to that molecule. So this is what it looks like. I start here with this molecule when I get to ibuprofen, and then I can sample small molecules that are small changes from that initial molecule. And based on that, you can kind of imagine, you can do like a step-by-step synthesis plan. And the other thing is now we have like also capacity to optimize things. We represent molecules, we have some geometry, and we can say like, how can I make a molecule more soluble, more drug-like? And so we can add some extra stuff to our models to make it just, make it more useful. And so, one example from the field is like this paper that came out in 2019. It's a really, really great work. People use deep learning to sort of find new molecules that can bind to a target. And in this case, this target is related to fibrosis and other diseases. They build a generative algorithm, generates a new molecule, a bunch of molecules that are drug targets or drug candidates, and they actually test it out in a lab. It's really it's really incredible work. They do it in like 21 days. Part of part of it was possible because because a lot of the work was led by in silico medicine. And when these models came out, there was also a lot of critiques. So some of the critiques, I think Derek Lowe from In the Pipeline has like a blog post around pharma-related things. I think he's really good. He has always opinionated takes. So like this is his opinionated take. Exactly when that paper came out is like, has AI discovered a new drug? Like guess, like if you have to make a question, it's probably no. I think, sort of what they found is that a lot of the compounds that were suggested were like very similar to things that already existed. And so then it begs the question, like, could you just ask a chemist to sort of propose the same thing? Do you need AI actually to do this? The other thing is sort of, the media coverage was less crowded. You have like, it's a company, they want to make money. So you want to make good PR for when you're actually spending money to do things. So, you just have to be critical when there's a lot of quotes. And, one of the things is like, they discovered a drug candidate, but like, actually checking out if it's actually something druggable, you have to go through a like multi-year process. So the real challenges was not really so much come up with a new molecule, it's like, can you make it here across human trials? Like, there's so many other complications to get to actually solving disease. So sometimes it's like claiming victory too early. Even then, it's like more rigorous than the majority of work that has been put out. People just do stuff with computers and say that we solved this when like it hasn't been solved yet. Another example, like the flip side on optimizing molecules, you could also imagine optimizing them to do like quote unquote bad stuff. Let's optimize them for toxicity or as a bioweapon, right? If you can solve a disease, can we like kind of create a disease, right? So based on that, there's like this paper that came out also a few years ago, dual use of AI-powered drug discovery. Basically what they said is like, look, using these same algorithms, we can generate molecules that are way more toxic. So what they did is they found generated 40,000 molecules that were optimized to just be more toxic than a nerve agent called VX. And so they were like, and a lot of people that publish this work also have like work in companies or consulting firms or started ones right after this. And so there's this idea of like, oh no, now AI can kind of make bioweapons. This is a little bit the coverage you'll see. So you just put AI bioweapons, chemical generative models, you'll find like a bunch. Like Radiolab called it 40,000 recipes of murder. I love Radiolab, but I just think the title's a little bit sensational. You know, like you'll have these kind of images of like biological stuff with like numbers, right? Often it's kind of making you think that things are more real than just something that's inside of a computer. And you know, there's a lot of money to be made in terms of security. So like, there's, you know, this is a big thing now. There's also like critiques about it. This is a think tank, but there's also like a lot of scientific critiques on the approach of can AI actually make molecules that are lethal. In general, it seems like, you know, some of the sort of critiques have been sort of that AI design toxicity is kind of trivial. We already had good AI models before, machine learning models. You can always generate molecules before. You don't need generative AI to do it. We already have a lot of lethal molecules in the world. Ebola is extremely lethal. If you get it, you know, it's like mortality rate is like 50%. And you know, often the problem is not so much coming up with the idea, but actually making the molecule. And so, you know, at least what they were thinking is like, we're at least 2027, at least one more year before you have autonomous AI design. But like the real thing is like, you know, physical abilities is really like often the bottleneck. Can somebody actually make these molecules? And we also have very like high quality scientists that can make molecules. So like if you really wanted to make molecules, if you really wanted to make bioweapons, you can pay a lot of money to maybe some scientists, right? I don't know if they would say yes or no, right? Money does weird things to people. So, you know, and especially now with LLMs and tool calling, like, you know, there's also studies on, well, can an LLM sort of come up with a plan to synthesize a molecule? Often we already know how to synthesize all these molecules. It's, you know, we have these tools. So often the bottleneck is not so much, you know, can we make this molecule? It's really like, can you like physically make it? We often know how to make these things, or if you train somebody or if you hire somebody, they will be able to come up with it. And even then, coming up with it is like really hard. When you're making molecules, like that can be an entire PhD set. You can make molecules, but you can have really bad yield. And so then you're like, your entire PhD is kind of, how do you optimize the yield of your process so you can actually make like, you know, kilos of whatever, you know, substance you want. So I guess like what I would say like with generative AI for like chemical scientific discovery is like some of the issues are sometimes illusions of discovery. Sometimes things are not tested exactly or comparatively. There's often real problems, but often the real problems are not necessarily in design space. We don't need more ideas, we need to make them. Like that's often what happens. And sometimes media coverage tends to be like lazy or sensational. You know, it's just like, that's just, I don't know how do you solve that. But I had a message here, but I don't know where it went. And so just to give you an example of, you know, kind of what are the real world constraints in a discovery campaign might be. So some of the work I've done is, you know, predicting smell. And what we build is what we call the digital representation of smell. So it's in the same way that we have a digital representation for color, red, green, and blue, 3 numbers, we have 63 numbers to represent smell. You know, we published this 3 years ago in Science. And we build an AI model, and it gives us this representation, and it can tell you, predicts certain things about molecules. It only predicts a single molecule, not a mixture, but we have work now for that. And you know, the common story and what we found is you get higher numbers. So AI numbers give us higher numbers on a computer. You know, that sounds great, but we also wanted to see like, okay, is this actually useful? So we also went out to test and discover new real molecules. So we were like, if I like a lot cucumbers and spicy stuff, so I was like, can we find a molecule that smells spicy and cucumbery? So what we did is like, given target labels, can we actually predict molecules that are not found in literature? Molecules that nobody supposedly has smelled before, and get people to smell it. We partnered with Monell Research Center with Joel Mainland. They have an incredible golden statue of a nose. You can even put your hand inside. The nostril's really big. And so we got into this task of trying to predict new molecules. And then you get real world challenges. These molecules can be toxic. You're gonna get people to smell these things. We were working at Google at the time, so part of it is like, we don't want to lose our jobs, so we need to make sure that, for PR purposes, Google doesn't, get bad PR around toxic molecules. We also want to make sure that they're like safe and environmentally friendly, and there's like storage, shipping, so there's like so many things that can go wrong. And then we train our models on professional perfumer data, but then we're like testing it on people from Philadelphia that are trained, right? And we're buying these molecules from eMolecules, which is like the Amazon of molecules, but for drug discovery. Like, this is not really the same as like fragrance molecules. So there's a data set shift. And overall, there's like molecules and trained human labor is expensive. So we were trying to really optimize how much money we spend on molecules, because we have to justify what we're doing to somebody. What does the molecule discovery pipeline look like? You come up with an idea, you make it, and you characterize it, and you then do like all these like iterations on that. The dream would be like, you can kind of do all this part with an AI model, and you'll be able to do this with like AI and automated robotics. So like a lot of the real problem will be like finding problems and setting them up in such a way that you can sort of have automated systems that help you do this. But the reality is that there's like so many failure modes. Like, is it in stock? When we were buying these molecules, a lot of the molecules come from Ukraine, and so the war was just getting started, and so there's like these big like scarcity problems around a lot of chemicals. Then you will also have a lot of problems around different models, intuitions, and ultimately somebody has to make it, so you have to convince somebody to make it. Even if you're paying them, you still have to convince people to make things, so it's all hard. And we're trying to measure something that has a lot of noise. When you smell stuff, if you ask somebody, they're gonna tell you different opinions, right? So it's a very personal, qualitative thing we're trying to measure. Because we wanted to be like very clear around our challenge or claim, we were like, we need to simplify all these decisions so it's like as easy as possible, so that it's more clear that this scientific claim is like very simple. And so basically we decided we need to find things that are very novel, very diverse, and surprising. And this is also like based on sort of some of the feedback we saw from a lot of people in the field. The same critique that you have from the bioweapon stuff, or not from the molecules that were discovered. They were like, this looks too similar to things that already exist. So we're like, we need to find a less similar thing. So based on this, we sort of created a bunch of, we decided we needed to pick 400 molecules. We did a back of the envelope calculation that this is how much money we had and how much data we can collect at a reasonable, in a reasonable way, and that gives us enough statistical power to make a claim over the best previous way of doing this. So we intentionally, this is our training set. We intentionally carve out a space where every molecule we pick has to be intentionally different from everything we trained it on. We also, we carve out spaces that are sort of diverse in this space. And then for every molecule we pick, we try to find something that is intentionally, structurally different, but should smell similar, and something that is structurally similar and does structurally similar, but smells very different. So this is a case where just changing this double bond will make it odorless. So this is like a big change in functionality. So we wanted something that was very challenging. And the extra challenge is this was happening during COVID. So this is like what a box would look like of all the molecules that were labeled. We did it across 8 rounds. People would get these box of molecules, and they would they would smell them. And this was like all online. And we have to measure that, like, kind of that people are reliable. Like, what if somebody got COVID and they can't smell anything? So we started with I can't remember how many, but it was more than 20, a panel of more than 20. We ended up with 16 at the end. Based on reliability, so we try to be diverse, but it's Philadelphia. So, and our data is already trained only on 2 perfumers from the US, so like there's already like a cultural bias around how things are described. Kind of what we find is basically, our model could make predictions that is better than any single person in this panel. So what we could claim is that, we can predict better than any single person inside of this panel. But once 2 people work together, they're actually better than our model. Just getting more people makes you get more reliable things. So, there's still room for improvement. And sort of what we tried to also show is that you couldn't do this 5 years ago. If you use like the best AI model, if you use the best whatever, like you wouldn't have been able to do it. So we wanted to show there was a clear difference in terms of technology. So it's very comparative. We allowed 2 models to compete, like something that was state of the art 5 years ago and ours, and we gave them the same opportunity to do the same thing. So something we did is like really this rigorous comparative part. So I guess in general, science is hard. And often, when we think about these things, we have to think about how do we create these stress tests to sort of, we're trying to trust these things. And so the more you test them out in very weird ways, you can just build a little bit more trust, and it just requires many iterations. In general, doing rigorous work is really expensive in terms of time and cost. This was like 5 years working on this. And often data often solves many issues. If you just have bigger data sets, that's often the real thing that solves it, not so much AI models. A lot of these issues, in some ways, disappear with money. If you have more money, you can collect more data. You can do more rigorous testing. But I don't know if I don't know if scientists need more money. I mean, there's always many caveats to that statement. So it's complicated. But yeah, so this is just like a broad sort of swap of how I think about these things. The closing thoughts is I think science is a human practice. So what this means is because it's human, we're going to have problems. They're not going to disappear. There's always going to be problems. AI exacerbates some of these problems because everything seems more magical. So you have a lot of big claims that sometimes are not well tested, or there's not enough time to test them, or not enough resources to test them. A lot of labs would want to create generative algorithms for chemistry and would want to test them out, but they don't have the resources to do it. And often we already know what the solution for these problems are. There's probably not a way to solve them, perfect way to solve them, but I think you have a lot of the problems you find in data replication and sort of reproducibility. It's not so much that we need more tools, or maybe sometimes tools help. It's more always a culture problem. How do you align a lot of people, right? You can think about researchers, scientists as kind of like cats. And how do you herd cats? It's kind of hard. Everybody wants to do what they want, right? And despite all these things, I think it's still useful and valuable to really think how do you create more equitable systems and all these things, right? Yeah. So any questions?
Good morning or afternoon. Thanks for your presentation. I think you've done a lot of really excellent work for the scientific community, and so I really appreciate the dedication that you and your team have provided, be it through Google or under your own expressions of science in your continued education since your bachelor's degree. I actually just wanted to bring up a point that when you asked about having us like chat amongst ourselves, what was something that was an ethics debate that's ongoing. The point that I thought of was the discrepancy, well, the gap that's continuing to grow wealth-wise between a lot of populations on this planet. Right now we're seeing such a huge shift in the world order, and there are individuals who will never be able to tap into their research creativity because of the lack of funds that they might have to be able to go to university or to be able to continue their education. So I really appreciate that you added that as a final point. Something I wanted to ask about, though, I'm not a chemist, but in terms of chemistry, how did you find data how did you clean your data? How did you screen your data, clean your data? What was your data sourcing process look like?
I mean, yeah, when you're working with with the aims of publishing something, then you basically have to find data that's already been published, so in a research journal, and you can use it. Or then you have to ask permission. So this data set, olfactory data sets, for example, there's public data sets, you can web scrape them. But kind of what we did is we talked to the owners of the data sets, and after like a year, we got their approval to get the data. And so it was basically, it took like, I don't know, 3 months to clean the data, where you basically go over all the rows, looking at the language, how do you convert this into an AI problem. It was 5,000 molecules, so basically 5,000 rows with textual descriptions, and so like making sure the text is useful. Yeah, and then we like made it available. So like, yeah, that's I think that's typically how people do it. You either, yeah, like it always has to be published mostly. Sometimes you can web scrape it, but it really depends on the type of data you're web scraping and the licenses from where you're web scraping stuff. Yeah.
Very interesting talk. Thank you so much for sharing. It's actually very interesting to me as well. Knowing a little bit about olfactory and like how smell affects us, I was just wondering, because it's the easiest way to manipulate hormones and like ANS, all that stuff. So I just want to know, how do you check for like the unknown before like starting your research, like actually like giving it to people, and like also how is your consent progress when you start like to like do they know what they're signing up for? Is it like something that's talked about in your consent?
So I'll answer first the second question and then the first one. So do they know what they're signing up for? Yes, I mean, I think that depends on the type of claim you're trying to make. Like if you're doing a psychological study where you're trying to like be careful about biases, you might not reveal everything. But typically what you do is you will have a contract that should cover you, and that, that should be ethical. Like as long as you're like not like torturing people in a bad way, like then it should be, I think there's ways of doing these things. In our case, like everybody knew what they were signing up for. Olfactory molecules are pretty safe in general, because gasoline is toxic, but you can smell it. And if you smell it a few times, it's not too bad. It's different if you're smelling it every day, but that's not what we're asking people to do. And so we worked with a toxicologist consultant to sort of sign off on all the molecules we were proposing, because we were getting new molecules. So we did a lot of research on that. Like we already knew that it wasn't going to be a real problem. The dosage is ultimately the problem, like how much of a dosage is. The gasoline example is one of those. Yeah, so in olfaction, it's not much of a problem. If something's going to be like a nerve agent, there's always clear signs for that. You wouldn't find it on a shelf being sold online. It would be different if you're making the molecules. Like new molecules that are not on any website in the world, right? That might be different. And how do you venture into the unknown? I guess like, yeah, I mean, ultimately you have to just see what everybody else has done before, and you're just like slowly moving around that, right? And you just try to take small steps, right? And make sure that you're kind of like validating yourself when you're moving across these steps. So you're kind of like, you know, and that's why you get like a toxicology consultant. You think about all the other considerations you need to have and try to account it in the best way possible, right? I think that would be my response. Yeah.
Thank you.
Okay, that's all the time that we have because we were running a little late. Thank you. That was an amazing talk. And thank you for your questions. Actually, I took a course with Professor last year, and it was really awesome. Same with some people in the audience, and so it's awesome to have him back.